So just in case I didn't get it on record yesterday for the distance learners, or maybe somebody's here today for the Google Meet that wasn't yesterday. The test retakes, we still have a person that hasn't taken the test yet. So if you want to do the retake and you're eligible, send me an email, talk to me in class if you're here, whatever you need to do, and I'll make that folder open to you, because I have to individually assign it when we get in this situation. This is one of my favorite sections that we do. And I know some of you are going to look at this and go, proving, don't think geometry, all right? Don't think the two-column proofs. When we talk about proving trigonometric identities, we're talking about, really, it's an algebraic feel to how we prove, well, lots of things that we're going to see today. And we all know from geometry that we are supposed to prove things before we use them. So this is kind of after the fact. We're going to see that there are a lot of identities that we have here that normally we probably wouldn't use. You know, they're not the Pythagorean identities and those types of situations, but they're things that could come in handy. And so if we want to use them, then we have to prove them. Now, I also want to let you know that when I did the homework answers, the worked out solutions for these, I tried to do it from the standpoint of, if somebody is struggling, how could I make this proof more obvious to them? So when you look at the worked out solutions, if you had a faster, quicker way, fantastic. That was not what I was going for when I was writing the homework worked out solutions. I was trying to write worked out solutions for somebody that's stuck and just needs help. So if you're looking at your answers and thinking, well, mine was 3 steps faster, that's probably the best way to do the proof. We're going to talk today about some of the strategies. And so I used those strategies when I went through and started thinking, if somebody has trouble, what would they need? So we're going to be able to apply strategies for proving identities, prove algebraic trigonometric identities, and disprove non-identities. So there's another little geometric spot for you there where you think, okay, how many counterexamples did we have to show that something doesn't work? And you just have to find one. That's all. So every once in a while, they'll give us something that's just not going to work out, just to check and see if we're paying attention. Now, one of the things I like about this section is that your book stops every once in a while and says, you know, here's a strategy. If you're having trouble with this, use this strategy, try this. So general strategies, the first box that they have here says, we know the proof begins with the expression on one side of the identity. So here's what we're going to do. We're going to pick the more complicated of the two sides, and we're going to work with it with trig and algebra to try to get it to look exactly like the other side. But you have to pick that side to start with, and you have to stick with it. So you pick one side, and you make your steps so that they will produce the other side of the equals. The proof ends when you have that expression on the other side. You've achieved your goal when you've shown, hey, all of this equals this on the other side. The proof in between, and this is huge, one step at a time. The proof in between consists of showing a sequence of expressions, each one easily seen to be equivalent to its preceding expression. No skipping steps, none. You have to show the little baby steps that show, here was my reasoning from why I went from this to this as you go through it. Now, we're going to start by just looking at an algebraic identity to get a feel for what we have to do with the trig. And in example 1, proving an algebraic identity, I think this is a little too obvious which side is the more complicated side, right? But that's what we should start with. We should start with the more complicated side. So I let whoever's grading my test know that by writing that side down. And that gives me a feel for what's going on. The first thing I noticed was this has subtraction, and people tend to make mistakes when you have subtraction in front of more than one term. So I'm probably going to want to change that to plus a negative. The other thing that I noticed here is that x squared minus 1 is factorable, and there's going to be some canceling that's going to be able to happen here. So let's see what happens with the canceling. I need the equals to break this up. I have to show, hey, this was what I chose. Now here's the first step that I'm going to complete by factoring. So we've got the difference of two squares, x plus 1 times the quantity x minus 1 over x minus 1, minus, still thinking I might have to change that to plus a negative, but let's just see how it works out. And then we have the x plus 1 and the x minus 1 all over x plus 1. Now I chose to go horizontal with this. You want to pick one way and stick with it. Every once in a while, a student will start off horizontal and then they'll go vertical from there. Has to be easily followed, so make sure that whatever method you pick, you stick with it as you go through. All right, so then we would show with a strike, not a scribble, because with the strike I can still see what you had underneath there, that we would have x plus 1 minus, and here the x plus 1s would cancel out, and x minus 1. Now I realize I'm not going to worry too much about changing that to plus a negative because I can just distribute it. So the first set of parentheses aren't really doing anything besides showing these two originally were together as a factor. But the second set, I have this negative in front, so I need to distribute it. And of course, we see x minus x is 0, and 1 plus 1 is 2. So every step is there. Somebody can easily grade this and see we knew what we were doing all the way through. We never would say, well, I'm just going to factor x plus 1 times x minus 1 in my head. Oh, this will cancel out, so I'm going to write down x plus 1 minus the quantity x minus 1 and just skip this step in here. Never do that, whether or not it's algebraic or trigonometric, and that's because we have to show each of those individual steps. General strategies 2, second box. Begin with the more complicated expression and work towards the less complicated expression. And I've got to get in front of here so that the Google Meters can see me too. When you're doing a proof, trigonometry or otherwise, it should start small, get a little bigger, and then pull itself back together as you get towards the end of the proof. If you start small, you get bigger, and you keep getting bigger, I got bad news for you. You better erase and start over. You went the wrong way. It should pull itself back at some point. So you want to watch for that. So more complicated expression, working towards the less complicated. If no other move suggests itself, you are stuck. Convert the entire thing to sine and cosine. The entire thing. Usually, that'll help people because we don't think in terms of the secondary trig functions. We just don't. You know, we learned sine, cosine, and tangent much earlier than we did cosecant, secant, and cotangent. So if you get stuck, change it. That's one of the things that I did very heavily on the worked out solutions for people that are stuck. Really went with sine and cosine a lot. Number 3, combine fractions by combining them over a common denominator. They give you a fraction. Think, well, what do you normally do with fractions if you have to add or subtract? You get a least common denominator and you put them together. So use your logic of things that you know that you've done in the past. So let's take a look. Proving an identity. Prove the identity tangent of x plus cotangent of x equals secant of x times cosecant of x. Now with this one, it might be a little hard to see, you know, which one of those seems like the more complicated. So easily you could just think, well, we've got a plus on the left-hand side. And tangent's one of our primary trig functions. These are the secondary ones. I'd much rather work with the primary trig functions to start with and figure out what's going on. So I'm going to start with tangent of x plus cotangent of x. And I'm not even really thinking ahead to what I'm supposed to get, but it sure is a nice plus to know what your answer's supposed to be. This is what we're supposed to end up with here in the end. So I started thinking, well, how could I put those together so that it would look more like a multiplication type of situation than an addition situation? Well, maybe I better think about sine and cosine and how that would work. So with tangent, it would be sine of x over cosine of x. And cotangent is just that upside down. So cosine of x over sine of x. Now if I want to get those together so I can actually do the addition, I have to find a least common denominator. And my least common denominator for these is going to be both cosine of x and sine of x. So this one will need a sine of x on the top and the bottom. And this one will need a cosine of x on the top and the bottom. So now my first fraction will say sine squared x over sine of x times cosine of x plus cosine squared x over sine of x cosine of x. Anybody see anything good that's going to happen here? Everybody see it? Okay, on the top there, we can now put those together. We've got sine squared x plus cosine squared x. Over sine of x times cosine of x. And I'm running out of room, and I don't want to break one of my own rules since I went vertical, because I write too big. So what did everybody see? When I asked you if you saw it earlier, when we put them together, what did you see? Your numerator is a 1. So do you think it's okay to skip that step? That'd be really silly, wouldn't it? Because part of what I just asked you was, did you see that? And if I had to ask you that, I need evidence that you did in fact see that sine squared x plus cosine squared x is 1 over sine of x cosine of x. Your test paper can't talk to me. This is the way you tell me you knew what you were doing. So now I think, okay, I think I'm getting closer. I've got secant x and cosecant x over there. Which one do we flip to get secant? Cosine. So if I do this and this, does that say secant x and cosecant x? It does, doesn't it? So I just broke it apart again. Once I had that one, broke it apart into a multiplication problem because that's what I had to get. And now, the very last step, I know it's obvious, but you have to write it. In fact, I'm going to go back and look and make sure they didn't put parentheses or anything like that on there so that it's a perfect match. It looks exactly like the right-hand side. And we have it. So it's not a two-column proof, not a geometry type of thinking. It's algebraic and trigonometric as we work through it. All right, let's go to B. With B, I see sine to the fourth of x minus cosine to the fourth of x. That is just not any help at all. That must be the most complicated side, because everything I know has squareds in it. So let's see. Hey, this is a difference of 2 squares. I could factor that and get that down to things that have squares in it. Well, I'm starting with this side. And yes, I didn't even read the other side yet. You know, I just started thinking about what math could I do to manipulate this and make it happen. But this is a difference of 2 squares. Something good happened there? What was the good thing? Owen? Sorry, Owen? We show that we recognize, hey, that's a Pythagorean identity. In fact, the big Pythagorean identity. So now we're down to sine squared x minus cosine squared x. Now I'm going to peek at that right side. Something's missing. My sine has to disappear because I need 2 cosine squared x. Let's see. So this is what I have that involves cosine squared x. I'm not supposed to have a sine squared x. Probably should do some substitution. So let me subtract cosine squared x from both sides. And substitute that in. Now I'm not going to write my black work that I just did up here in my proof, but I'm using it to think about what I can do to substitute. So instead of sine squared x now, I'm going to put 1 minus cosine squared x minus cosine squared x. Hey, wait a second. If you've got minus cosine squared x and you have another minus cosine squared x, you've got minus 2 cosine squared x. And that's what we needed to get. So some of this, I mean, if you're thinking, I don't know that I would have got all of that by myself, Cedar Home. You will. It takes practice. It just takes a little while for you to start thinking, what do I have for formulas versus what did they give me? And how do I get it there? So it just takes a little practice. We're going to get that practice. This one I think is just a little mean. Identifying and proving an identity. Because it says, match this function with one of the following. So we don't know which one of those is supposed to work or not. So that would be really mean. I mean, we could start this one and, get 8 steps deep and find out, well, this one doesn't work. Or same thing here. It looks pretty basic, 1 over the secant of x, but we could do a whole lot of work and not know. So how do you figure out beforehand which one you should really go after? And the key to that is going to be graphing. Because if this is one side of the equation and this is the other, when we graph them, they have to graph exactly the same. They look very different right now, but when we graph them, they have to be exactly the same. So these are monsters to type in, by the way. And that's because, remember, our calculator doesn't have a secant button. It doesn't have the secondary trig functions. So this one has to go in with a ton of parentheses. One set, 2 sets, boom. One set, 2 sets. There's the 1 over cosine of x. There it is, plus 1. And then the whole thing, like so. Making sure I have matching parentheses there. And then, these would be a little easier. With cotangent, it is easiest on your graphing calculator to just do 1 over tangent. So here's what we're hoping to see. I'm hoping I don't have to punch in the third one, 1 over secant of x, although that'd be the easiest one to punch in. And yes, I cheated and did it this morning because I was really worried as I punched it in up here that my smartboard would crash and, we'd have all kinds of trouble to try to figure out which one was which. So here is the 1 over parentheses, parentheses, 1 minus cosine of x, parentheses, minus 1. So there's the first little fraction, plus, and there is the second fraction. lots of parentheses to get it to do it right. But it's going to save us a lot of time because, you know, we'll know in advance which one of these is going to be the match. And then y sub 2 is 2 cotangent, 1 over the tangent of x, and then cosecant, 1 over the sine of x. And I put the third one in, but again, hoping the first two match so that we don't even have to go to that third one. Still punching? Okay, let me give you some time. So like I said, this time is worth it, you know, if you're very careful about punching in those fractions to begin with. Would it be better if I had my handwritten one back up there for you right now? Or is this working? Okay, leave this. If you're done punching it in, quick check and make sure that you're in radians mode. For the window, I just did negative 2 pi to 2 pi. It's up to you. You can make it a little bigger if you wanted to. And then negative 3 to 3 for the y's. Make sure I can see what I need to see. And then graph. Oh, I want you to see the original. How about if I change this? Maybe it'll start over and graph again. No, maybe it'll graph it. Shoot. Well, if you have a color one, what you saw was a blue one first, and then probably a red one went right over the top of it. So then we know this is the one. This is where we need to go with this graph. We don't need to punch in the third one. This is supposed to do it right here. So now, we've got to start with this monster and get it to look like this. I'm going to need more space. Again, this has addition in it. We know we have to get to this, which is multiplication. So the obvious choice would be, hey, let's find an LCD and put these together and then see what we can do. Unfortunately, the LCD is kind of a whopper. So we're going to have to use the secant of x minus 1 and the secant of x plus 1. But that's already got me thinking ahead. I want you to think for a second about what we get if we were to take secant of x minus 1 times secant of x plus 1, and whether or not that would be a good thing. Get something with secant squared, right? Don't we have a Pythagorean identity that has that in there? Well, then let's give that a try. So now we have secant of x plus 1 over, and I would say, hey, I know I have a Pythagorean identity that deals with this, so I am going to go ahead and make this secant squared x minus 1 right now. instead of leaving it separated. Normally, we would leave it separated until the end to see if we could cancel anything. All right, well, they have the same denominator. So we can go ahead and do that addition. Forgot my little C here. And we see the plus 1 and the minus 1 are gone. So now, think about that secant squared. And somewhere on my paper I have written, come on, Blue. And I need to get secant squared. Secant squared is which of the primary trig functions? Reciprocal? So that would mean I should divide this whole thing by cosine squared. So sine over cosine, that's going to be tangent squared. Cosine over cosine would be 1. So if I subtract my 1 from both sides, now I can replace that secant squared x minus 1 with tangent squared x. Now I want you to take a look at where we're supposed to go and see whether or not we've gotten ourselves a little bit closer to that. See, the 2 is there now. That's a good thing, right? So at this point, we kind of think, well, how should we get the rest of this to happen? Well, we got to break it apart so that we'll have cotangent and cosecant. So every once in a while, it's not a bad idea to do what we call an educated cheat. And this part, again, is something you'd probably erase. But over here, let's see what this would look like with sine and cosine. So it would look like that. 2 cosine of x over sine of x, and 1 over sine of x. Well, let's see if we can get there and make that happen. So we have 2 secant of x over tangent squared x. So let's change this to multiplying by the reciprocal. And think about what we can do with it. Secant, which one of the trig functions do we flip? So 1 over tangent squared x, we could make that 1 over sine squared x over cosine squared x. And put this into terms of sine and cosine. And now we can multiply by the reciprocal. And we see we're going to have a cosine that'll cancel out of there. I don't want to drop that totally. So let's go see where we were trying to go with this. Then we wanted a cosine of x over sine of x, and a 1 over sine of x. Can we break it apart to get that? So we'll have our 2 cosine sine now we have what we wanted. We needed 2 cotangent x cosecant x. Now here's why us using the graphing calculator was so important. I'm guessing people might have given up somewhere around here if we didn't know where we had to go with this. So it got bigger, and then it pulled itself back and got smaller in the end. So one of the strategies I was showing here again was if you can get things in terms of cosine and sine, something that you might not have seen before may just pop up and you'll realize, hey, I've got this. I know where this is going to go. And this part is I know I call it an educated cheat, but it is actually a way that proofs are done. One of the strategies is start from both ends of the proof and make it meet somewhere in the middle if they get tough. So that is an additional strategy to make things match. So general strategies 3. We've had a lot of boxes with strategies in here. Use the algebraic identity, difference of two squares here, sum and difference, a squared minus b squared, to set up applications of the Pythagorean identities. We know we're supposed to have squareds. Make it happen. Always be mindful of the target expression. Where am I supposed to go? Have I pulled too far away from that? Did I go in the wrong direction? Should I go back? And keep that. Favor manipulations that bring you closer to your goal, to where you can get. So example 4 says, setting up a difference of squares, proving this identity. And really, with this one, again, you might think, well, both sides are kind of, equally bad, but this one doesn't have any addition or subtraction in the denominator. So the right side is a little bit easier. So we should start with the left side. Now, like it said, be a good idea to set up a difference of squares to make this happen. I mean, they're giving us a big tip here. And to do that, I'd realize, oh yeah, it might be helpful to multiply this times 1 plus the sine of t, because then I'll get a squared in there. And I could just use my basic Pythagorean identity. All right, so I'm going to start with this. But I'm going to multiply by 1, because remember, that is really multiplying by 1. We're just manipulating the way it looks, so that I can start to see some squareds in my denominator. So up here on the top, I've got my little cosine of t times 1 plus the sine of t. And on the bottom, sum and difference pattern, I will now have 1 minus sine squared t. Hey, 1 minus sine squared t. Isn't that just our Pythagorean identity, sine squared plus cosine squared equals 1, manipulated a little bit? So if we subtracted sine squared from both sides, that'd give us cosine squared, right? Let's see if that helps. Did it help? Big time, right? What do you see? A little canceling? And there it is. So once you've done a few of these, you really want to listen to that little voice in your head that says, wait a second, I think if I just use sine squared t plus cosine squared t equals 1, I could get something good to happen here. And pull it back together until you get that right-hand side. Now, this one doesn't have a box, but these are some that we added here because we know they're great strategies for working through trig proofs. Multiply by a clever form of conjugate over conjugate to set up a difference of squares and a Pythagorean substitution. And while they called it, they've got the sum and difference pattern, everything up there, this is truly the conjugate of our denominator right here. When you have the same first and last term, but you just change the sign. That helps tons. And then expand only the conjugates. Notice up here I did not distribute this cosine of t. I was thinking in advance, okay, if I can get a cosine squared in the bottom, then that'll cancel out and good things will happen. So once you expand the conjugates and leave the other side of the fraction factored, divide out any of those common factors that we possibly can. Now, this one takes a while, so I had best check the clock. We're good. Should be able to get through this one. Now, this is what I called the educated cheat before. Better spell educated right. That would be a crime. Working from both sides. Sometimes our proofs just become so complicated that we kind of lose track where everything is. And here's why that's going to happen with this one. Do you see any primary trig functions up there? And that's when you kind of go, oh my goodness, there's going to be a lot of reciprocals here. So, looking at the left and the right side, the left side has that 1 plus cosecant of theta in the denominator, so that would be nice to work with. And I see that this one is factored. That factoring happens while we're in the process of trying to get what we need. So I should be starting over here. And this one is phi, and I know that's going to be hard. We haven't used phi a lot, but you have to stick with whatever they used. So I know everybody's going to want to put a horizontal line through there and make it theta. All right. So we need to figure out what on earth we're going to do with this. And there is a cotangent theta on the other side, but there's also secant and tangent. So what's the go-to? Well, we have this 1 plus cosecant of phi down here. Would not be a bad place to start. We also see we've got this cotangent squared of phi up there. We might be able to use a Pythagorean identity to do something about that one. So I think I'm going to start up here and see if there's anything interesting that happens when I'm using and I want to know about cotangent. So I think about how I can get cotangent, and cotangent comes from cosine squared divided by sine squared. So I'll have to divide the whole thing by sine squared. And I get that. So first thing to try would be to say, you know what, I can replace this with something that has cosecant in it instead. So if I subtract 1 from both sides, at least then I'll have stuff that has cosecant in it. Like so. Hey, wait a second. That's the difference of 2 squares. Oh, am I getting that close? Oh, you guys have to go. Crud. Well, it's recorded, okay? Does anybody see anything good that would happen if we factored cosecant squared minus 1 on the top there? Yes, we'll be able to do some canceling. Yeah, they have to go early to talk to Mr. Mitchner. Everybody else, you're trapped. Oh, come on, Blue. Behave yourself. All I did was forget my C. So at this point, we talked about how the steps are important. I'm not going to make you reverse this to show me that you know they're exactly the same to cancel them out. I mean, that's something everybody knows. So we just say, here's the plus 1, here's the 1 plus. That's definitely going to work. Come on, Smart Bird. There we go. And you get here, and you start to think, how on earth am I any closer to that right-hand side than I was when I started? Because things got smaller, which was great, but maybe I lost too much. Because I'm supposed to get all of this when I'm done. Well, this is the spot where you say, I'm going to do the educated cheat. I'm going to work from the other side. I'm going to change everything into cosine and sine and see what I have, and then see if I can get there with the way I've gone. So we've got cotangent of phi times secant of phi minus tangent of phi. And we're going to work backwards and hope that we can meet up with what we have over here. So cotangent is cosine of phi over sine of phi. What primary trig function do we flip for secant? Okay. And then tangent is what over what? Sine over cosine. So now, well, let's see what that would look like if we actually distributed that cosine over sine. So here the cosines would drop out. Oh, in the back there, cosine and sine would cancel out. What's 1 over sine? Well, look at that. That'll meet right up with what we have over here. So now we're going to use this backwards to get to what we need. That is absolutely a strategy for trig proofs. Absolutely. When the proof starts to feel like it's getting away from you, go from the other end. So this is 1 over sine of phi. And now I'm writing theta. Minus 1. Then we'll break it up into those two primary trig functions of cosine and sine. And all the way back up to what we were supposed to get on the other side. Now, I'm not going to encourage you to erase. I did have a professor in college that said, once you've done all of this, this is, the educated cheat, and he'd say, erase all of that so nobody can see it. But I'm going to want to see your work, when you're doing your test, so I can give you partial credit for anything that you've done. Just keep it separate from what you've done with your proof, and then you'll be okay, because I'll be able to see it and know you knew exactly what you were doing when you went through it. So that one was a little tough. That one is a little sticky. And when it gets a little sticky, then you think, all right, let me try that educated cheat. I'll start from both ends and try to get this to meet. And that was where I'd hoped we would get to today. So you could start working on some of this. Lots of strategies, lots of different ways to go at them. Like I said, remember that the worked out solutions, what I tried to do was do work for folks that maybe are getting stuck. So you might find an easier, shorter proof. That's fantastic. I really wanted to gear those worked out solutions to people that are struggling at this point.